Let's do another optimization problem. So taking a look once again at our steps to optimization here on the screen, and remembering that our goal here is going to be to create an objective function using whatever constraints are given in the problem, and then to use that function and what we know about calculus to find the maximum or minimum, whatever it is that we're looking for. So let's take a look at this example. So suppose we have an offshore well. It's located 5 kilometers away from the closest point on a straight shoreline. The oil is to be pumped to a location in a city 8 kilometers east along the shoreline, and pipe must be laid to pump oil to the city. Cost $1 million per kilometer to lay pipe underwater and $500,000 per kilometer to lay pipe under the ground versus under the water. Where should we plan to exit the water and begin laying pipe underground instead of underwater to minimize the cost to lay pipe? Lots of info given here, but we are trying to minimize a cost. So let's start by writing that down. So the goal here is to minimize. Right? Whenever we're looking to optimize, we've got to figure out, are we trying to maximize or minimize? So we want to minimize the cost to lay pipe, okay, to oil. Now, there is a lot going on here, and so I think that a picture is going to serve us well on this particular situation. So we've got some offshore well. So let's just, here's our offshore well. And it obviously gets drilled down into the water, so I'm going to make it. So we've got some offshore well out in the water, and then from that point, so here's the, this is obviously water, and from that point to a straight shore, it says it's 5 kilometers away from the closest point on a straight shore. So let's suppose that this is the land. Okay. So 5 kilometers away from a straight shore, this distance right here is 5 kilometers. And distance would be measured at a right angle. So we know that that is a right angle. If it's the closest point, it would have to be the right angle. And then east from where you come out, let's call that point P, the oil is going to be pumped to a location that is 8 kilometers east to a city that's 8 kilometers east along the shoreline. So east would be this direction. So from point P, let's call this point Q over here, and this distance from P, where we exited the water, to Q is 8 kilometers. And this is the town. There's a factory over here where we're going to pump the oil. So that's somewhere over there is a city or a town. Oh, I think it said city. So here's the city where we got to get the oil. Okay, so now we got a couple of choices. We could go straight to shore and then along the shoreline. That would be one choice. Okay, we could go straight from the well all the way under the water and lay the pipe straight to the city. That would be a second choice. Okay. Or we could go partially underwater, hit the ground, and then to the city. Okay, on the ground. So go partially underwater, partially on the ground. We could go straight down the 5 kilometers, go the least amount of distance underwater, and then 8 kilometers to the city. Or we could go straight all the way underwater and go straight from the well to the city. But remember, it costs a lot more to lay this pipe underwater than it does to lay it on the underground. So what we want to do is we want to figure out what would be the point at which we should exit the water so that we have the least cost. So to do that, let's go ahead and draw one more line here. And let's just suppose this will be our variable. Let's suppose that we were to exit. This is going to be our exit point. Okay, so what if we were to exit right there? I was going to call it X, but I want to actually label this distance from here to here as X. So from here to here is going to be X, this distance from here to here. So what if we exit a distance of X away from that point P, which would make this distance from that point to Q 8 minus x. Okay? So that x equals the distance from point P. Remember, point P is where we is the shortest distance. It's the point on the shore that is the shortest distance to the well. Okay, so that's point on shore. And then 8 minus x would be the distance to the city. And then what would this be right here? Well, that's the distance we would have to lay the pipe, right? So that would be the distance. We're thinking we go from the well to this point and then to town. So that would be that little question mark right there. That would be the distance we would have to lay pipe under the water. But what would that be in our scenario? Well, we could use Pythagorean theorem here, and that would actually have to just simply be, let's get my pen instead of my highlighter, that would have to be the square root of x squared plus 25, okay? Just using Pythagorean theorem. So the square root, so this is the distance to the city where pipe would be underground, and the square root of x squared plus 25 would be the distance underwater. Not the distance, let's say the distance where pipe is underwater. So it's the distance where pipe would be underwater. Okay, now we're going to create a cost function here, but before we do a cost function, I just want to note those two other scenarios that we mentioned. So note that x can be between 0 and 8. X is a distance between 0 and 8. And it could actually be equal to both 0 and 8. If x was actually equal to 0, if x was equal to 0, that would be the scenario where we went straight to the shore. Okay? So that's the scenario where we go straight to shore from the well. And if we were at 8, if x was actually 8, that would be the scenario where we go, if x equals 8, that's the scenario where we go straight to town, or straight to the city. Underwater. Okay? The whole way. We would end up being underwater the whole way. So if x were actually equal to 8, that would be the scenario where we go straight from the well to the city. Okay, so I just wanted to mention that will come into play. This inequality will come into play when we're doing our domain of our cost function. But I did want to mention that we could actually have those scenarios where we're equal to 0 and we're equal to 8. And that would be the first two scenarios that I mentioned when I was drawing my picture. All right. So what then is going to be the actual cost to lay this pipe? And we got to think about what the costs were given to us here. And I want to keep that picture on the page. Okay, so it turns out that our cost function is going to be a function of where we come out on the water, right? Where we come out of the water, which we've labeled on the picture using that x. That's going to be our diagram there that we're going to use to create this cost function. So the cost function is going to be, it's going to be a cost underwater. Write it out in words first, plus the cost of pipe underwater plus the cost of pipe underground. And so let's go ahead and let C of x be the cost in millions, because I don't want to carry all those zeros, okay, in millions of dollars. Okay, so the cost to lay, so C of x, the cost to lay pipe under the water, well, the distance under the water is this square root of x squared plus 25. So this is distance underwater. Well, each kilometer underwater cost $1 million. So it's going to end up being 1 million, but I'm going to write it as 1 because this is in millions of dollars, times the square root of x squared plus 25. That's how many kilometers we're going to go under the water. Plus, and then it cost 500,000. So that is a half of a million. So I'm going to write that as 0.05, half of a million. And what's the distance under the ground? Well, this piece right here is the distance underground. So the distance underground is that 8 minus x. Wherever we come out, we're going to have 8 minus x kilometers left to get us to the city. So that's going to be 8 minus x. So it's going to be 500,000, which is represented in millions as half of a million, so 0.5 million times 8 minus x. And that gives us the cost. That is our optimizing function. That's our objective function, the function that we want to optimize. We want to minimize that function. Now, the next step after we've created a function is to always talk about the domain of that function. And once again, we've talked about this in a lot of the examples. The functions that we create, often outside of context, have a different domain than they have with the context. And so again, we have to think about the fact that x has some restrictions here based on the context. It wouldn't make any sense for x to go negative. X going negative would mean we'd go this direction, which doesn't make any sense. We're not going to go backwards and add extra distance to the city. That doesn't make any sense. So obviously x has to be greater than 0. We've already mentioned that just in the context of our picture, that x has to be between 0 and 8. And it is inclusive of the 0 and 8. X equaling 0, we could go straight to the shore and then lay 8 kilometers underground. That would minimize the distance that we would have to go underwater. But I don't know if that's the best scenario. Or we could maximize the distance underwater, right? We could go straight from the well all the way to the city. But there's a cost factor in here that we're going to have to use some calculus to figure out what's the best. So back to the domain. The domain in the context, right? We do always have to think about in context. The domain in the context of this problem is going to be x has to be between 0 and 8, inclusive of 0 and 8, or we could write that as an interval, and as an interval it would be a closed interval from 0 to 8. So notice that for the domain is actually a closed interval, and that's going to play in when we get into looking at the max and the min. But before we do that, to determine maxes and mins on a closed interval, so let's just make a little note here. Note, because the first time we've had a closed interval for the domain. So to determine, in our examples, to determine max mins, we should say absolute maxes and mins, because that's what we want. When we're optimizing, we want to know what the absolute maximum or the absolute minimum is. So determine absolute max or mins on a closed interval. We have to go back to our extreme value theorem, and we have to consider not just the critical points, but also the endpoints. So consider critical points and, I'll underline that, endpoints. Okay. And so I'm going to go ahead and just I'm going to make that a little note that we want to remember across all of our optimization problems. If we're on a closed interval, we don't want to forget that we have to check those endpoints too, that our absolute maxes or mins can occur at those endpoints. So just as a reminder, that comes from a scenario like this. If you're looking at a continuous function on a closed interval, notice that the absolute, this goes back a while, the absolute min occurs at this local minimum, but the absolute max is actually occurring at an endpoint. Okay? So that just goes back and kind of a quick reminder that we can have absolute maxes and mins at endpoints. So on closed intervals, we have to also remember to consider the endpoints. All right. So let's get back to it. So now let's find the minimum cost. Find the minimum, I added a little extra letter. Find the minimum cost. And this is where all of that up to this point has simply been a little pre-calculus, a little work on drawing a diagram and coming up with a cost function. But now we're going to find the minimum cost. I'm going to keep my cost function up there at the top. Actually zoom in a little so I have a little bit of space here. And we're going to take the derivative and find the critical point. So we're going to take the derivative of that cost function. The derivative is going to be 1/2 times x squared plus 25 to the minus 1/2 times chain rule, so times 2x, derivative of the inside, plus 0.5 times the derivative of 8 minus x, which is just -1. And then I'm going to go ahead and simplify that. Simplifying that becomes x over the square root of x squared plus 25 minus, I'm going to write that as 1/2, minus 1/2. And now I need to find critical points. Notice that this function is actually never undefined, so let's consider when it would be equal to 0. So when does x over the square root of x squared plus 25 minus 1/2 equals 0? And notice it's never undefined because the denominator here, that x squared plus 25, for all values of x is positive. So it's never even 0. Okay, so solving this, let's add the 1/2. So we've got x over the square root of x squared plus 25 equals 1/2. Do a little cross multiplying there. So 2x equals the square root of x squared plus 25. Square both sides, get rid of that root, so that 4x squared equals x squared plus 25. Subtract the x squared, so I get 3x squared equals 25. So that x squared equals 25 over 3, and x is equal to plus or minus 5 over root 3. X being a distance, though, of course, right? That's out of domain. And just to simplify that a little bit, let's make that 5 root 3 over 3, which just for reference for our sign chart here, as well as just the context, that's about 2.89. And that is in kilometers, by the way. Remember, x was a distance from that point P, the closest point to the well on the shore. Okay, so 2.89 is what we've gotten for x. So just back to the picture to remember. So now once we've found the critical points, let's go ahead and use a little sign chart. Let's look at the sign of the derivative. And that point, remembering that we do have that restricted domain, so we're from 0 to 8. We're over here at positive 5 root 3 over 3, which is approximately 2.89. And let's look at the signs to show that that is, in fact, a minimum. And again, it will be a local minimum because its derivative is equal to 0, horizontal tangent. So if we take the derivative, and if I pick a number, so like if I pick a number like 1 and I plug that into the derivative, you could do the calculations, but it turns out that that is negative, and I find that it is decreasing. Pick something like 5 and plug that into the derivative there, and you're going to find that you get positive and it is increasing. Okay? Which means, of course, if we decrease till we get to a horizontal tangent, and then we start to increase, that's going to make this point right here a minimum. So we have shown that this is a local minimum. And I'm going to illustrate that point. I want to be clear that that's a local minimum because remember my point here, and it's all highlighted in red. To determine the absolute max or min, we also have to consider those two extremes, right? The 0 and the 8. We have to consider the scenario where we go straight to the shore when x is 0 and then 8 kilometers underground. We also have to consider the scenario where we go straight from the well to the city with no pipe underground. So we do have to consider those. So let's do that right here. So here's the last step. We want to consider, since it's a closed interval, we have to also consider endpoints. We've just shown that we have a local minimum. But what about, is that local minimum my absolute minimum? I don't know until I check the endpoints. So I go to my little table and I'm going to compare the cost function at 0, at 2.89, and at 8. So the two extremes are in there as well. So those are the two endpoints. Okay? So checking, we have to add in the two endpoints and check those against the cost. So the cost function is up there. It's up in the upper corner. I just ahead of time, I just plugged this into that cost function. It turns out that if I plug in 0, what I get back is 9, and this is in millions, by the way, I get back 9 million. If I plug in 2.89, I get back 8.33 approximately million. If I plug in 8, I get back 9.43 million. And notice in this scenario that the absolute minimum does occur at that critical point, but we have to check. Okay? Switch up how much it costs. Like if for whatever reason it becomes more expensive to lay pipe underground, that would definitely change what's happening here. If it became more expensive or less expensive to lay pipe underwater, like if there was changes in these costs, slight changes in these costs would definitely change our result. And so the absolute minimum is to exit the water 2.89 kilometers, actually, I think I might have said miles, but kilometers from the point P, which is the closest point to the well on the shore. Okay? And so let's go ahead and summarize that. So the absolute, let's put it up here with the picture. So the absolute minimum cost to lay pipe is 8.33 million by exiting the water at, it's actually a 5√3/3, which is approximately 2.89 kilometers from point P. And I won't redefine point P, we defined it in the picture, but point P is the point that is the closest point on the shore to the well. And that is our answer. Okay, let's try to get it all on the page here. So we set up the picture, we talked about the domain and how the two extremes give us that 0 and that 8, created a cost function using the costs that were given, and in the end, we found not only the local minimum, but we checked that local minimum against the endpoints, and you do need to do that. You need to check your endpoints if you have a closed interval.